December 1941. A military motor pool somewhere in the American Midwest, 3 days after Pearl Harbor. The temperature hovers just above freezing. Mechanics work under portable lights, their breath visible in the cold air. Sergeant James Mitchell slides under a 2-ton cargo truck, the third one this week with the same problem. His flashlight beam cuts through the darkness beneath the chassis, finding the oil drain plug. He positions the collection pan and loosens the plug with his wrench. The oil that pours out tells a story. It should flow smooth and amber even after use. Instead, it comes out thick, nearly black, with a gritty texture that makes Mitchell's stomach sink. He's seen this before, too many times. He lets a few drops fall onto his palm and rubs them between his fingers. The oil feels wrong, grainy, abrasive, like liquid sandpaper. He holds his fingers up to the light and sees what he expected: metal particles, tiny flecks of steel and aluminum suspended in the oil, carbon deposits, combustion residue, all of it circulating through the engine like a slow-acting poison. This truck has maybe another 1,000 miles before something catastrophic happens, maybe less if they push it hard. The bearings are already compromised. The cylinder walls are being scored with every revolution, and there are 10,000 more trucks just like it, all running on oil that's slowly transforming from lubricant to abrasive compound. Mitchell wipes his hands on a rag and thinks about the war everyone knows is coming to them soon. How are they supposed to fight across oceans and continents when their engines keep dying before they even leave American soil? The problem was invisible, but absolutely deadly. Inside every internal combustion engine, oil serves as the lifeblood of the mechanical system. It circulates through a closed network of passages, lubricating pistons as they slide up and down in cylinders, coating crankshafts as they rotate at thousands of revolutions per minute, protecting camshafts as they open and close valves with precise timing, and forming protective films on bearing surfaces where metal components spin against each other under tremendous pressure and heat. But that oil doesn't stay clean. The very process of combustion creates contamination. When fuel burns in the cylinders, it produces carbon deposits. Some of this carbon escapes past the piston rings and enters the oil. Metal surfaces grinding against each other, despite lubrication, produce microscopic particles. Steel wearing against steel creates iron particles. Aluminum pistons sliding in iron cylinders produce aluminum particles. These particles are measured in microns, invisible to the naked eye individually, but collectively devastating. Dust enters through air intakes. Moisture condenses in the crankcase. Combustion byproducts include acids that degrade the oil's chemical properties. All of this contamination ends up suspended in the oil, circulating through the engine with every pump cycle. And without effective filtration, this contaminated oil becomes an agent of destruction. The abrasive particles act like microscopic grinding wheels. They score cylinder walls, creating grooves that allow combustion gases to escape and oil to enter the combustion chamber. They embed themselves in bearing surfaces, creating friction points that generate excessive heat. Heat breaks down the oil's lubricating properties, reducing its viscosity and its ability to form protective films. As lubrication fails, metal begins to contact metal directly. Friction increases exponentially. Temperatures spike. Bearings run dry and seize. When a bearing seizes, the engine stops, sometimes gradually, with increasing noise and vibration giving warning, sometimes catastrophically, with connecting rods breaking and punching through engine blocks. In the early decades of the 20th century, this wasn't a problem anyone had truly solved. Engine designers accepted contamination as inevitable. Engines were expected to wear out relatively quickly. Frequent rebuilds were considered normal maintenance. Oil changes happened every few hundred miles. Because the oil became so contaminated, it turned into sludge. Mechanics drained the black, gritty fluid and replaced it with fresh oil, knowing the cycle would repeat. The contamination problem was managed through frequent maintenance, not through prevention. For civilian vehicles driven gently on paved roads and maintained regularly by their owners or local mechanics, this approach was manageable, if expensive and time-consuming. But war doesn't allow for frequent maintenance. War demands engines that run continuously under conditions that would destroy civilian vehicles. War requires trucks to drive hundreds of miles through desert sandstorms where dust infiltration is constant. War needs tanks to operate in sub-zero Arctic conditions where oil thickens and contamination accelerates. War depends on jeeps bouncing through jungle trails, where humidity and heat create the perfect environment for oil degradation. America in 1941 faced a crisis that most people didn't recognize because it was technical and unglamorous. The country had industrial capacity that dwarfed any other nation. It had steel mills running at full capacity, assembly lines that could be converted from civilian to military production, and a workforce ready to build whatever the war required. What it didn't have were oil filters that actually worked well enough to keep engines alive under sustained combat conditions. And without reliable engines, all that industrial capacity meant nothing. Tanks that couldn't move were just expensive metal boxes. Trucks that broke down were obstacles, not transportation. Aircraft with engine failures killed their crews. The first serious attempts at solving engine oil contamination came in the 1920s, a full generation before the war. Two inventors working independently of the major automotive manufacturers saw the problem clearly. George Greenhalgh and Ernest Sweetland understood that engines were destroying themselves from within, and they believed filtration was the answer. They developed something they called the purolator, a name derived from the concept of pure oil later. The idea was elegantly simple. Take dirty oil from the engine, pass it through a filtering medium that traps contaminants, and return clean oil to continue lubricating. The oil would be purified, hence, pure oil later. The purolator represented the first modern approach to oil filtration. Previous attempts had used simple screens or settling chambers, relying on gravity to separate particles from oil. These methods were minimally effective. The purolator used an actual filtering element, a medium with pores small enough to trap particles while allowing oil to flow through. It was a genuine innovation, and it worked. Engines equipped with purolators lasted longer than unfiltered engines. Oil stayed cleaner. Bearing wear decreased. The technology proved the concept that filtration could extend engine life significantly, but the purolator and similar early filters developed through the 1920s and 1930s had significant limitations that prevented them from becoming universal solutions. They were expensive to manufacture, requiring precision machining and quality materials. This made them luxury accessories rather than standard equipment. They required regular maintenance that was time-consuming and technically demanding. The filtering media needed to be removed, cleaned, and reinstalled, a process that could take an hour or more. The filtering media itself couldn't handle the finest particles, the ones measured in single-digit microns that caused the most insidious damage to bearing surfaces. And perhaps most importantly, they weren't standard equipment on vehicles. Most cars and trucks in the 1920s and 1930s left factories without any filtration system at all. Oil filters were aftermarket accessories, something you purchased separately and had installed if you could afford it, and if you understood why it mattered. For the average civilian driver, the value proposition wasn't obvious. Yes, an oil filter extended engine life, but if you were planning to trade in your car every few years anyway, why spend money on an expensive accessory? If you changed your oil frequently, which was recommended practice, wasn't that good enough? The automotive industry didn't push filtration because it added cost to vehicles, and most consumers didn't demand it. So filtration remained a niche technology through the 1930s, used by some commercial operators and enthusiasts, but not by the mass market. For civilian vehicles driven gently and maintained regularly, this situation was manageable, if not ideal. For military vehicles expected to operate under the most brutal conditions imaginable, often for days or weeks without proper maintenance, it was a disaster waiting to happen. The technology that existed in 1941 simply wasn't good enough for what the war would demand. The military knew this. Reports from early campaigns from the North African desert and the Pacific Islands documented engine failure rates that were alarming. Vehicles were being lost not to enemy action but to mechanical failure. Something had to change. Into this gap stepped two chemists from Providence, Rhode Island, who had been thinking about oil filtration for a decade. Frederick Franklin and T. Edward Oldham weren't military men. They weren't thinking about war when they founded Fram Corporation in the early 1930s. They were thinking about a technical problem that fascinated them as chemists and engineers. How do you filter oil effectively without creating so much flow resistance that the oil can't circulate properly? How do you make a filter element that's easy to replace so that maintenance becomes simple enough for ordinary vehicle owners? How do you do it cheaply enough that the filter becomes affordable rather than a luxury item? These weren't trivial questions. Oil filtration involves complex fluid dynamics. Oil is viscous, meaning it resists flow. Pass it through a filtering medium with small pores, and the resistance increases dramatically. Increase resistance too much, and the oil pump can't maintain adequate pressure. Oil pressure drops, lubrication fails, and the engine destroys itself even faster than it would without filtration. So the filtering medium has to balance two competing requirements: pores small enough to trap harmful particles, but open enough to allow adequate oil flow. The replacement question was equally important. If changing a filter required an hour of work and specialized tools, most people wouldn't do it. The filter would clog, flow would be restricted, and the filtration system would become a liability rather than an asset. The filter had to be designed so that replacement was quick and simple, something that could be done with basic tools in a few minutes. And the cost question was fundamental. If the filter cost more than most people were willing to spend, it would remain a niche product. Mass adoption required mass affordability. Franklin and Oldham's answer to these challenges was the F1 filter, introduced in the early 1930s. It used a replaceable element design that was revolutionary in its simplicity. The filter housing remained permanently mounted on the engine. The filtering element inside the housing was designed to be removed and replaced. Instead of disassembling the entire filter assembly, cleaning metal screens with solvents, and reassembling everything with new gaskets, you simply unscrewed the housing, pulled out the old element, dropped in a new one, and screwed the housing back on. The entire process took minutes instead of an hour. The F1 wasn't perfect. The filtering media was still relatively coarse by modern standards. It couldn't trap the finest particles. But it was significantly better than what existed before, and it was practical. Fram sold the F1 to automotive aftermarket dealers and directly to vehicle owners who understood the value of filtration. The company built a reputation for quality and innovation. Their filters worked, they were reliable, and they were improving with each iteration as Franklin and Oldham continued their research into filtering media and housing design. Through the 1930s, Fram expanded steadily. They developed relationships with automotive manufacturers, convincing some to offer Fram filters as factory-installed options. Their filters started appearing on higher-end vehicles where buyers were willing to pay for premium features. The company remained small compared to the giant automotive suppliers like Delco or AC, but they were growing, they were profitable, and most importantly, they were learning things about oil filtration that would matter enormously when war came. By 1940, Fram had been refining oil filter technology for nearly a decade. They understood the chemistry of oil breakdown in ways that few other organizations did. They knew which particle sizes caused the most damage to which engine components. They had tested dozens of different filtering media, learning what worked under various conditions and what failed. They understood flow dynamics, pressure drops, and the relationship between filtering efficiency and oil circulation. This accumulated knowledge, built up through years of incremental improvement and careful testing, positioned them to solve a problem that was about to become critical to national survival. When America entered World War II in December 1941, the military's vehicle requirements exploded overnight. The mobilization plans called for producing trucks, jeeps, tanks, half-tracks, armored cars, and countless other vehicles in quantities that seemed impossible. Hundreds of thousands of vehicles. Eventually millions. All of them needed engines that could run for extended periods under conditions that would destroy civilian vehicles in days. Consider the operational requirements. A cargo truck in the North African campaign might drive hundreds of miles through desert sand so fine it penetrated every seal and gasket. Temperatures inside engine compartments exceeded 150 degrees Fahrenheit. The air was thick with dust. Every breath of air the engine took brought in particles that would contaminate the oil. Maintenance facilities were hundreds of miles away. Spare parts were scarce. Mechanics were overwhelmed. The truck had to keep running, or supplies didn't reach the front lines. A tank in the European theater might operate continuously for days during an offensive. The engine ran constantly, not just for movement but to power electrical systems, turret rotation, and other equipment. Oil temperatures spiked. Contamination accumulated rapidly, and there was no opportunity to stop for an oil change in the middle of a battle. The engine had to survive until the offensive paused. A Jeep in the Pacific Islands bounced through jungle trails where humidity approached 100% and temperatures never dropped below 80 degrees. Moisture condensed in the crankcase, acids formed, corrosion accelerated. The combination of heat, humidity, and constant vibration from rough terrain created an environment where everything failed faster than it should. The existing oil filter technology couldn't handle these conditions. Metal screen filters, the most common type available in 1941, clogged quickly in dusty environments. Once clogged, they restricted oil flow, causing pressure drops that led to lubrication failure. They were heavy, adding unnecessary weight to vehicles that needed to be as light as possible for transport and maneuverability. They were expensive to manufacture at a time when every penny of war production budget had to be justified, and they required skilled labor to maintain properly, something that was in desperately short supply as experienced mechanics were spread thin across multiple theaters of operation. The military needed something fundamentally better. They needed filters that could trap finer particles, down to the single-digit micron range where bearing damage occurred. They needed filters that were cheap enough to produce in massive quantities without straining war production resources. They needed filters that were simple enough that a soldier with minimal training could replace them in field conditions, possibly at night, possibly under fire. They needed filters that would keep working when everything else was falling apart. Fram's engineers understood the challenge with unusual clarity. Because they had been working on these exact problems for a decade, they knew what didn't work. They knew where the limitations were, and they had been experimenting with alternative filtering media that might overcome those limitations. The war didn't create their research program. It accelerated it and gave it urgent purpose. The breakthrough came in 1942, less than a year after Pearl Harbor. Fram introduced a new line of oil filters called Filcron. The name was derived from filter and cron, though the exact etymology was never clearly documented. What mattered wasn't the name. What mattered was the filtering media. Instead of metal screens or woven cloth, Fram used specially treated paper. Paper. The idea seemed absurd to anyone who understood engines. Paper disintegrates when wet. Paper tears easily. Paper is fragile, the opposite of what you want inside an engine where temperatures reach 200 degrees Fahrenheit, where oil pressure pulses constantly with every revolution, where the environment is hostile to anything delicate. But Fram's chemists, drawing on years of research into materials science, had figured out how to make paper work in conditions where it shouldn't survive. They treated the paper with synthetic resins that made it resistant to oil and heat. The resins bonded with the paper fibers, creating a composite material that retained paper's filtering properties while gaining durability. They engineered the paper's fiber structure at a microscopic level to create pores of specific sizes. Too large, and harmful particles would pass through. Too small, and oil flow would be restricted. They found the optimal balance through extensive testing. They pleated the paper in an accordion-like pattern to maximize surface area. A flat sheet of paper has limited filtering capacity. Once the surface is covered with trapped particles, flow restriction increases and efficiency drops. But pleat that same sheet into dozens of folds, and you multiply the effective surface area many times over. Each filter element contained several square feet of filtering media folded into a compact cylinder. This gave Filcron filters far more filtering capacity than flat media could provide in the same physical space. And they designed the housing to support the paper element structurally, preventing it from collapsing under pressure. The paper element was held in place by perforated metal cylinders on both the inside and outside. These support structures were strong enough to resist oil pressure, but perforated enough to allow oil to flow through to the paper media. The entire assembly was engineered to survive the vibration, pressure fluctuations, and temperature extremes of engine operation. The result was remarkable in ways that became clear only through extensive testing. Filcron filters could trap particles down to sizes that metal screens missed entirely. The particles that caused the most bearing damage, the microscopic metal fragments and carbon deposits measured in single-digit microns, were captured. Before they could circulate through the engine, oil stayed cleaner for longer periods. Analysis of oil samples from engines equipped with Filcron filters showed contamination levels dramatically lower than engines with metal screen filters or no filters at all. Engines lasted longer. Maintenance intervals could be extended. A truck that might have needed an engine rebuild after 10,000 miles with poor filtration could run 30,000 miles or more with effective filtration. That difference was enormous in military logistics. It meant fewer replacement engines needed to be manufactured, shipped, and installed. It meant vehicles stayed operational longer. It meant the same number of mechanics could support more vehicles because they spent less time on repairs. And the filters were cheap to produce. Paper cost a fraction of what metal screens cost. The raw materials were abundant and didn't compete with other war production needs. Steel was precious in 1942, needed for ships, tanks, and weapons, paper was available. Manufacturing was faster than metal filter production. A Filcron filter element could be produced in minutes on relatively simple equipment. A metal screen filter required precision machining, welding, and quality control processes that took hours. When you needed millions of filters, that difference in production time was the difference between meeting demand and falling short. The field advantages were just as important as the technical performance. A Filcron element weighed ounces instead of pounds. Soldiers could carry spare filter elements easily in their packs or in vehicle storage compartments. Weight mattered in military logistics. Every pound of equipment had to be transported, often across oceans and then across battlefields. Lighter filters meant more could be carried in the same space. Replacement was simple enough that it became routine maintenance, rather than a specialized task. You didn't need special tools beyond a basic wrench. You didn't need technical training beyond basic instruction. Unscrew the filter housing, pull out the old element, drop in the new one, screw the housing back on, check for leaks. Done. The entire process took 5 minutes. Even in combat conditions, even with limited light and limited time, even with hands shaking from cold or fear, a soldier could change an oil filter. That simplicity was itself an innovation. Complex systems fail in war. Simple systems survive. The military tested Filcron filters extensively before committing to mass adoption. They couldn't afford to bet on unproven technology. They ran controlled tests comparing Filcron filters to existing metal screen filters and to no filtration at all. They installed them in trucks and drove those trucks through desert proving grounds, measuring engine wear and oil contamination at regular intervals. They installed them in tanks and ran those tanks continuously for days, simulating combat operations. They installed them in jeeps and subjected those jeeps to vibration tests that replicated thousands of miles of rough terrain driving. The filters worked. Not just marginally better than existing technology, but dramatically better. Engines that should have failed after a few hundred miles of desert driving kept running for thousands. Maintenance crews reported dramatic reductions in bearing failures, the most common cause of engine seizure. Oil analysis showed contamination levels that were a fraction of what metal screen filters achieved. The data was overwhelming. Filcron filters represented a genuine breakthrough. Fram ramped up production to meet military demand. The company's factories in Providence, Rhode Island, ran multiple shifts around the clock. New production lines were added. Workers were hired and trained. Raw materials were prioritized through war production allocation systems. The federal government designated Fram as an essential war contractor, giving them access to materials and labor that might otherwise have been unavailable. By late 1942, less than a year after the Filcron introduction, the filters were being installed in military vehicles across all branches of service. Army trucks got them, Marine Corps jeeps got them, Navy vehicles got them, tank destroyers, half-tracks, armored cars, all of them received Filcron filters as standard equipment. By 1943, they were so thoroughly integrated into military vehicle production that it became difficult to find a military vehicle without one. The impact was exactly what the military needed, though it manifested in ways that were difficult to quantify precisely. Vehicles became more reliable. That reliability translated into better logistics. Supplies reached front lines more consistently. Offensives could be sustained longer because vehicles didn't break down as frequently. Maintenance burdens decreased, allowing the same number of mechanics to support larger numbers of vehicles. These effects aggregated across hundreds of thousands of vehicles operating for years. The advantage wasn't dramatic in any single instance. No battle was won because one truck had a better oil filter. No campaign succeeded or failed based on filtration technology. But aggregated across the entire war effort, the cumulative effect was enormous. Every engine that didn't fail meant one more vehicle operational. Every operational vehicle meant supplies reached where they were needed. Supplies at the front meant offensives could continue. Continued offensives meant victory came sooner. The humble paper oil filter, invisible inside its housing, contributed to winning the war as surely as any weapon, though its contribution was measured in prevented failures rather than achieved victories. After the war ended in 1945, Fram's paper filter technology transitioned seamlessly to civilian applications. Automotive manufacturers, having seen the performance advantages in military vehicles, adopted Filcron filters for civilian production. The company that had been a small Rhode Island operation before the war became a household name. Fram filters appeared in virtually every American car and truck produced in the late 1940s and 1950s. The technology spread globally as American automotive designs influenced manufacturers worldwide. Other companies licensed the design or developed their own versions, but the fundamental concept remained the same. Specially treated paper, pleated for maximum surface area, housed in a simple replaceable cartridge. The innovation endured because it was genuinely superior to everything that came before, not just adequate for wartime emergency use. Paper filters captured smaller particles than any previous technology. They were cheaper to manufacture, making them economically viable for mass production. They were easier to replace, making maintenance simple enough that ordinary vehicle owners could do it themselves. They worked reliably under conditions that destroyed other filter types. And as engines became more sophisticated through the 1950s and beyond, requiring cleaner oil to protect tighter tolerances and higher operating pressures, paper filters adapted and improved while maintaining the same basic design. Modern oil filters in 2024 use synthetic filtering media and advanced housing designs that would have seemed like science fiction to Frederick Franklin and T. Edward Oldham. They incorporate anti-drainback valves that prevent oil from draining out of the filter when the engine is shut off. They include bypass systems that allow oil to flow even if the filter becomes completely clogged, preventing total lubrication failure. They're engineered for specific applications, from small motorcycle engines to massive industrial diesel engines producing thousands of horsepower. But the core principle hasn't changed in over 80 years. Pleated filtering media in a replaceable cartridge, trapping contaminants before they can damage engine components. What Fram invented in 1942 still protects engines today. The story of Fram's paper oil filter illustrates something important about technological innovation that often gets overlooked in favor of more dramatic narratives. The solution to a critical problem doesn't always require exotic materials or revolutionary engineering breakthroughs. Sometimes it requires seeing a familiar material in a new way. Paper was everywhere in 1942. It was cheap, abundant, and well understood. What wasn't understood was how to make it work inside an engine. Fram's chemists figured that out through careful research, systematic testing, and chemical treatment that transformed ordinary paper into an extraordinary filtering medium. The wartime context accelerated development and provided unlimited demand, but the innovation would have happened eventually because the need was real and growing. Engines were becoming more powerful and more complex throughout the 1930s and 1940s. Higher compression ratios meant higher operating temperatures. Higher operating temperatures meant faster oil degradation. Faster oil degradation meant more contamination. More contamination meant engines needed better filtration. Metal screen filters couldn't provide it. Someone would have developed paper filters eventually. Fram happened to be the company that did it first, at exactly the moment when it mattered most. There's a broader lesson here about how wars drive innovation, though not always in the ways people expect. The urgency of wartime production, the essentially unlimited budgets for anything that contributes to victory, the willingness to try unconventional solutions because conventional approaches aren't working, all of these factors accelerate technological development. But the innovations that endure beyond the war are the ones that solve real problems, not just wartime problems. Fram's paper filter worked in 1942 because it was genuinely better than existing technology, not because it was good enough for an emergency. That's why it's still used today. Long after the war that drove its development has faded into history. The mechanics who cursed over contaminated oil in December 1941 got their solution in 1942, not from some dramatic breakthrough in materials science, not from some massive government research program, from two chemists in Rhode Island who understood oil chemistry and who figured out how to make paper work in an engine. They solved the invisible problem. They gave America's military the reliable engines it needed to win a global war. And they created a technology that would protect engines for generations to come. When you change the oil filter in your car today, you're using technology that helped win World War II. The filter element you unscrew and throw away is a direct descendant of Fram's Filcron design from 1942. The pleated paper inside, treated with resins to resist oil and heat, works on the same principles Frederick Franklin and T. Edward Oldham developed more than 80 years ago. The housing design, the replaceable cartridge concept, the simplicity of maintenance that allows you to change your own filter in your driveway with basic tools, all of it traces back to that wartime innovation. America didn't have effective oil filters in 1941. By 1942, it had the best oil filters in the world, and that advantage contributed to victory in ways that are difficult to measure, but impossible to dismiss. Fram's paper core technology kept engines running when they should have failed. It reduced maintenance burdens when skilled mechanics were desperately scarce. It extended vehicle life when replacement vehicles were needed faster than factories could build them. The innovation was quiet, unglamorous, invisible to everyone except the mechanics who installed the filters and the soldiers whose vehicles kept running because of them. Wars are won with weapons and tactics and strategy, but they're also won with logistics and reliability, and the thousand small technologies that keep armies moving. Fram made sure American armies could move, and that made all the difference. If you enjoyed this story of hidden innovation, subscribe to the channel for more untold engineering history. Hit the like button if you learned something new today, and drop a comment below. What other invisible technologies do you think shaped the modern world? Let's discuss.